Okay, now we are coming to the next part of learning of analyzing statically indeterminate beams. As I have briefed you earlier, we have two methods to approach statically indeterminate beams. One is force method, other one is deflection method or stiffness method. Force method is a simple one, but it has some limitations in terms of number of unknowns can be resolved. But stiffness method or deflection method can be used for any number of unknowns. And under deflection method, we have discussed how to approach a statically indeterminate beam using slope deflection method. And we are going to discuss how can we use moment distribution method to solve statically indeterminate beams. In addition to this, you have already covered these 4 sections, which helps you to solve statically determinate beams. And in statically determinate beams, you can use these methods to determine deflection and slope. So now we'll look at this moment distribution method. So like the slope deflection method, moment distribution method can be used only for analysis of continuous beams and frames, taking into account their bending deformations only. This method, which was originally developed by Hardy-Cross in 1924, was the most widely used method for analysis of structures since 1930 till 1960s. In early 70s, with the increasing availability of computers, the use of moment distribution method has declined in favor of computer-oriented matrix methods of analysis. You will learn about these matrix methods in next year, or probably you might get some introduction in the next semester, but you will learn in detail in year 3. Although computer packages are widely used to analyze structures, you should remember that still for small buildings and structures, people use moment distribution method because it gives you a reasonable or a reasonably well accurate results, and also it gives you a feel of how these problems are solved. So if you get a chance to work in a small design office, there's a very high chance that you will be asked to use moment distribution method to solve or to design or to analyze and design small and medium size buildings. So it's very important that you become familiarized with this method, because this has a huge benefit for every civil engineer and a design engineer. So moment distribution method is also used for preliminary designs, for checking, and also it's used to check the results of computer analysis. I think this is something I just want to emphasize, checking the results of computerized analysis. Using computer to analyze a problem is easy, but you have to validate the results, because whatever you feed into the computer is given as the result. So if your input is not correct, your output will not be correct as well. So in such situations, you can use these simple methods like moment distribution method to cross-check your results obtained using computer analysis. So now let's look at how can we approach this problem. This is very similar to slope deflection method where we derive the equation. Okay, so if you can recall the slope deflection equation that we have derived, say when we apply a moment m which rotates this point by theta, we derived an equation. I can show you that so here this is our discussion on slope deflection method. So here we have applied a moment and rotated this theta b, and then we got a relationship between b and ab, and finally we have developed this relationship, that is MAB is 4EA theta A over L. So when you rotate this by theta A, the MAB requires it to rotate by theta A is 4EIL into theta A. So that is what written here. So if you are applying a moment that rotates this by theta, that 4EA theta A over L is the required moment to rotate this point by an angle theta. And the carryover moment is for half of that, so that is 2EI L over theta A. Now there is something you can see that, okay, to rotate an angle theta A, you need 4EI over L into theta A. Suppose if this theta A is a unity, so if you want to rotate this by 1 unit rotation, then the moment you require is 4EI over L. So if you want to rotate point A by a unit rotation, the amount of moment required the amount of moment required to rotate that point A by unit rotation is 4EI over L. And this 4EI over L is called the stiffness of the beam against the rotation or against the bending. So bending stiffness K is equal to the moment that must be applied at an end of a member to cause a unit rotation. So if you look at this beam, the bending stiffness of the beam is 4EI over L. Now if you consider a pin-pin condition, so if you develop fixed pin condition, so this is an internal support, this is the far end is pin. So if you develop a conjugate beam and if you solve it, you will find that M is equal to 3EI over L into theta A. So now if you recall this, what we did, we took this beam and we have applied a moment like this. So now if I do a similar solution to this, so here let me take this space. So if I have a beam, okay, and I'm applying, this is a continuous end, this is a far end, this is a pin, okay, and this is a pin, internal pin, and I rotate this by an angle theta, so it takes a shape like this. Okay, it's theta m. So now here there is no restraining moment because the pin, it can freely rotate. So if I plot the bending moment diagram, so, or if I write down this RA, this is RB, so RA plus RB is equal to 0. So if you take moment by A, M plus RB into L is equal to 0, so RB is equal to minus M over L. So now if you plot the bending moment diagram, so here it is hogging, so negative, so that is M. Here the moment is 0. Now if I draw M over E diagram, so that M over E diagram is going to look like, so that is M over EI. So M over minus M over EI. Okay, this is the M over EI diagram. So internal pin is becoming, so this is a pin support, so it remains pin. Here it is a pin support, far end pin also remaining pin. So you can remember that here this one remained as a pin, but here it was a free end because it is a fixed condition. So this is remaining M over EI, and this is the M over EI diagram. So if you draw the conjugate beam, so in the conjugate beam, this is the conjugate beam, so this support is remaining a pin, so with the reaction RA, so RA is M over L, so here it is a pin again, and you have the moment M over EI is acting like a load. Okay, acting like a load. So this is M over EI. So if I get the equilibrium condition, here it is theta A, here is theta B. So because the theta A, theta B, because the slope in the real, in a conjugate beam is equal to the the shear force in the conjugate beam is equal to the slope of the real beam. So the slope here is theta A, slope here is theta B, and so that is why I have marked these reactions as theta A and theta B. So if I balance theta A plus theta B minus half into M over EI into L, so that's the area, half into M over EI into L, this area is equal to 0. So theta A plus theta B is M into L over 2 EI. And if I take moment uh, by A, so that becomes theta B into L. So counterclockwise, theta B into L at A, so that is counterclockwise, minus the area is half into M over into L, and the distance to that is 1/3 L. See, so this L cancels off, so theta B is equal to 1/6 I into N. Okay, so this half into, and then 1/3 L is the distance from here. So theta B is 1/6 M over EIL, and theta A is M over L over 2 over EI minus. So if you look at this, so let me move this down a bit. Okay, so since theta A plus theta B is equal to M into L over 2 EI, that comes from this equation 1, equation 2. So substitute 2 in 1, so then theta A becomes ML over 2 EI minus ML over 6 EI. That is the common base is 6 EI, and so 3 ml minus ml, so that is 2 ml over 6 EI. Okay, so that is, if I further shift this a bit, M is equal to, so this is 3 EI, M is equal to 3 EI over L into theta. That is what's shown here. So 3 EI over L into theta A is M, so that is the M here. Okay, so if the far end is pinned, the stiffness is 3 EI over L. If the far end is fixed, the stiffness is 4 EI over L. So that's what we need to know. Okay, so and the carryover moment, so that is say when you have M applied here, there is a resisting moment MBA should be there, so that is normally half of the M applied here. Okay, so if MAB, if MBA is 2 EI over L, MAB is 4 EI over L, so MBA is half of MAB, so this is half of MAB, so there is 4 EI theta, okay? And here it is half of MAB. So that is this is called carryover moment. That is when you rotate this by moment, when you apply a moment M here, it rotates by theta, and here there's a tendency to rotate as well, but that rotation is prevented because there is a fixed end. So the fixed end is applying a moment that prevents that rotation. So that applied moment is called carryover moment, which is half of this moment we applied here. This we have proved already using slope deflection equations. So that is for fixed end condition. So when the far end, so we call this is the end where we apply the moment, and this is called the far end. So when the far end is fixed, you have a carryover moment. But when the far end is pinned, you don't have a carryover moment because this pin will allow the point B to rotate. So there is no carryover moment here at B. So there is no carryover moment at B because it's a pin. So consider this, if you consider for BA, MBA is 0, therefore the carryover moment is 0 when far end is pin, and is M by 2 when it is fixed. So if it is a fixed, so that if you consider a portion of the beam and the one end is an internal point, another end is a far end. Far end means the edge of the beam. Okay, you need to be very clear, edge of the beam, either edge of the beam. So if the far end is fixed, the moment applied at the far end to prevent the rotation is M by 2. But if the far end is pinned like this, it is 0. So carryover factors are 0 when the far end is pinned, half when far end is fixed. So then we are coming to something called distribution factor. So this is again used in moment distribution method, as you hear from the name of the method, distribution method. So you distribute the moment, or the distribute the resistance. So when analyzing a structure by a moment distribution method, an important question that arises is how to distribute a moment applied at a joint among the various members connected to that joint. So if a point, say if this point is rotating by an angle theta, then there is a moment that rotates this by theta, and for that there is a resistance as well. So the moment is balanced, so there is a resistance. So that resistance is not equal for all three members. It may be equal, it may not be equal, but we are going to see how to decide it, how much moment is applied by each member to prevent this rotation. So the moment M is resisted by all three members. Since the rotation theta is same for all three members, so if you look at this member C, here is a far end is fixed. So here the rotation M. So if there is a moment M, so the component, so MBA, so MBC here, if you look at CB, C is fixed, B is internal point, so MBC is 4EI L2, so this is L2 and I2, so 4EI2 over L2 into theta is the contribution of the moment from MBC. Similarly, contribution from MBA is 4EI1 over L1 into theta, but here it is far end is pin. This is a pin joint. So here the moment M is 3EI3 over L3 into theta. So it's in the ratio of the stiffness. So each of these elements, so if you have a rotation occurring here at theta, all three members will rotate by theta, but the resistance for the rotation is given by each member, and that may differ, may not differ, and if it would differ, it is differing because of different length of the segment we consider and the different stiffness of the member. So here if you consider this member BC, the length is L2, stiffness is I2. If you consider BD, length is L3, stiffness is I3. If you consider AB, the length is L1, stiffness is I1. So it's in the ratio of that. So if MBA is 4EI I1 L1 into theta. Why 4EI? Because this end is fixed. Because of MBD, so that is a BD, this portion. Here 3EI 3L3 into theta. Why it's 3EI 3L3? Because this point is pin. So when the far end is pin, we have seen that the stiffness of the segment is 3EI over L. So if you consider MBC, it is 4EI over L into theta. So if you rework this one, so you can write this K AB, that is the stiffness of the segment AB, as 4EI 1 over L1. So that is the KAB, KBA, both are same. KBD is 3EI 3 over L3, and KBC is 4EI2 over L2. So these are the stiffnesses, and we mark them by K into theta. So K into theta, K is the stiffness against the rotation, theta is the angle by which it rotated. So that is the moment induced or moment carried by that element. So now if you look at this moment M, so M is equal to MBA plus MBD plus MBC. So all the component for moments, you sum it, it is equal to M, because the M is applied that rotates this point, and the internal ones are MBA, MBD and MBC. So that's why M is equal to MBA plus MBD plus MBC. So if I substitute these, M is equal to, if I substitute BA, it's KBA into theta, here is KBD into theta, here is KBC into theta. So theta is common, so KBA, KBD, KBC into theta. So as you can see that the component, each component, so the amount carried by each segment is given by the stiffness of that segment into the rotation. So these are the main elements we need to know, that is the stiffness of each section and the distribution factor. Now for example, if you have a moment M, the portion carried by BA, the distribution, say the distribution factor AB is equal to KAB plus KAB plus K. So that is, it's slightly different. Now that is the other important aspect, so the distribution factor. So let me shift this a little bit. Okay, so the distribution factor. Now if you consider this junction B, so distribution factor BA, so that is this BA, so that corresponds to MBA, so that is KBA over KBA plus KBD plus KBC. The reason is distribution factor is MBA over M. So that derived, this comes from distribution factor is factor BA is equal to MBA over M. So MBA is KBA into theta, M is KBA plus KBD KBC into theta. So theta cancels out. The distribution factor is KBA over KBA plus KBD plus KBC. So that is for KBA, and similarly KBC, you will have the distribution factor is KBC over KBA plus KBD plus KBC, and if you consider this one, it is KBD over KBA plus KBD plus KBC. So that is the distribution factor, how in much proportion the moment is distributed between the three elements that is connected at that joint. So two things are important for us. One is the distribution factor. So the distribution factor is what we have discussed here. The other one is your moment carrying capacity of each of these segments. Now let's consider, okay, if this is an internal support, we can consider this distribution factor like that. But how about the fixed support? So in a fixed support at A, you have a fixed support and you have a element. So that is B. So the AB, KAB has a value. So that is 4EI 1 L1 over. So that is 4EI 1 over L1. That is the KAB. 4EI 1 over L1. So what is the other element connected in this junction? So here we have a fixed support and an element connected together. So if you consider the K support A, so KA, so stiffness of support K is infinity. Okay, because it's a very stiff support, it's a fixed joint, so the K stiffness of support K is support A is infinity. So this is stiffness of support A. And if you consider the distribution factor of A, DF support A, that is infinity over some value that is 0. So which means that support A will not distribute anything to the far end. It will absorb everything. Okay, so that is the way we approach this problem. So we have a simple problem that we can solve. I think we have solved this using slope deflection equation as well. So the solution to this one I will upload as a separate video.